February 1953, England's East Coast. 6 Caterpillar D8s crawl onto a broken sea embankment. While the North Sea waits for the next tide, one of those tractors will reach the breach edge and feel the bank move under its tracks. That was the moment the repair stopped being earth-moving. To understand why 6 Caterpillar D8s ended up fighting the sea on a shattered English embankment, go back to the east coast of England in the winter of 1953. The flood itself had already done the first part of the damage. What remained was the second crisis, slower, colder, and in some ways more dangerous. Once the water broke through the seawalls, it did not simply arrive and leave. It tore channels through embankments, filled low farmland with salt water, undermined roads, drowned drainage systems, and turned stable ground into a moving slurry of clay, silt, and broken fill. In Lincolnshire, Norfolk, Essex, and across other low-lying districts facing the North Sea, the problem was no longer just survival, it was containment. Every tidal cycle threatened to reopen what had only just been patched. Every hour of delay meant more erosion, more inland flooding, more pressure on villages, pumping stations, roads, and rail links already operating at the edge of failure. The sea had entered the land, now the land had to be taken back. That mattered because eastern England in 1953 was built around embankments, drainage cuts, sluices, and reclaimed marshland that depended on control. Much of this country lay only a few feet above normal high water, and some sections effectively existed below the level of the sea, unless banks, gates, and pumps kept the system working. Once a breach formed, the flood did not behave like a simple pool. It moved with the tide. It scoured. It widened. It attacked from both directions. Water rushing inland on the flood tide could carve one shape into the bank. Water draining back out could cut another. What looked like a damaged gap at low water could become a full hydraulic channel when the sea returned. The men directing the emergency works understood one thing immediately. Hand labor alone would not close those openings fast enough. Trucks could bring fill, but trucks needed roads, and many roads had been washed, softened, or blocked by debris. Excavators could dig, but a breach in tidal ground demanded constant pushing, shaping, and compacting under conditions that changed by the hour. They needed track-type tractors, heavy ones, machines that could move spoil, force rock and clay into place, and keep working where wheels would sink. That is where the Caterpillar D8 entered the story. By the early 1950s, the D8 was already established as one of the most capable heavy crawler tractors in British civil work. Depending on configuration, these machines weighed roughly 18 to 20 tons and carried the kind of low-speed pushing power that mattered more than speed on a broken embankment. In dry earth-moving, they were formidable. In tidal mud, they were something else. Not invulnerable, but often the only machine with any realistic chance of staying on top long enough to do useful work. 6 of them were brought into one of the breach-closing operations on the East Coast after the flood. The exact geography varied from report to report because emergency work in those days was often documented by district engineers, local authorities, military support units, and newspaper summaries rather than one single national machine log. But the operational picture is clear. A tidal embankment had been opened. The gap had to be narrowed, then choked, then rebuilt before the next sequence of high tides made the damage permanent. On paper, the plan was straightforward. Use available borrow material from the landward side, bring in additional fill where possible, and push the mass into the breach from both flanks. As the opening narrowed, heavier material would be added to resist scour. Then the crest could be raised and dressed before the next major tide. In the field, it did not work so neatly. The first problem was access. The embankment itself had been damaged by overtopping and washout, which meant the D8s were being asked to travel on structures whose internal strength was no longer certain. An earthen sea bank can look intact from the surface while its core has already been loosened by seepage and undercutting. Under those conditions, a crawler tractor does not merely ride the bank, it tests it. Every pass is a load case. The second problem was the material. Freshly broken embankment fill is not uniform. Some of it is compacted clay, some is saturated silt, some is top-layer turf and root mass, some is rubble. Once salt water and returning current disturb that mixture, its behavior changes fast. The blade could carry the load. The ground beneath it could not always carry the machine delivering it. Then there was the tide. A breach repair in tidal country is not a continuous job. It is a race conducted in intervals. At low water, the opening exposes mud, torn slopes, and whatever foundation remains. Men and machines move in, material is pushed, the line begins to take shape. Then the tide turns. Water rises into the cut, finds every weakness in the unfinished closure, and starts removing what has just been placed. If the fill is too light, it washes. If it is too loose, it liquefies. If the shoulders are not tied in firmly enough, the sea simply goes around the new work and attacks the bank again. That was the environment facing the 6 D8s, not an ordinary construction site, a damaged hydraulic system under repeated assault. Contemporary accounts from flood recovery across eastern England make clear how severe the national pressure was. More than 300 people died in England in the flood. Tens of thousands were displaced. Large areas of agricultural land were contaminated by salt water. Sea defenses had failed in multiple counties. Railway embankments, roads, drainage channels, and pumping infrastructure were all under threat. The machine work at each breach was local. The consequences were not, so the D8s were not there for spectacle. They were there because if the breach stayed open, the sea kept a door inland. By the time the machines were lined up for the main push phases, the operation had settled into a brutal rhythm. Work the ebb, push during the window, retreat before the water rose too high, come back and do it again. Each cycle carried more risk because every attempt required the tractors to edge closer to the unstable lip of the gap. And with each pass, the bank changed under them. The numbers looked manageable. The reality was not. 6 Caterpillar D8s could move an extraordinary volume of earth in ordinary ground, but this was not ordinary ground, and the sea was not waiting for the engineers to finish. In the breach, hydraulic force was deciding which material stayed and which disappeared. That was the deeper problem. The machines were powerful enough to build a closure. They had to build it faster than the tide could erase it, and then the ground changed again. Then the shoulder of the bank began to move under the lead tractor. Not all at once. That was the danger. A tidal embankment rarely announces failure with a dramatic collapse at the start. First the surface softens. Then one track settles slightly deeper than the other. The blade load feels heavier, not because the machine has found more resistance ahead, but because the bank itself is no longer giving full support beneath the tractor. Operators know that sensation immediately. The engine still has power. The machine no longer has ground. One D8 backed out in time. Another did not, as fill was pushed toward the narrowing gap. The outer edge of the embankment slumped into the breach channel and took part of the working platform with it. The tractor dropped nose first, blade low, tracks losing level together as the saturated shoulder sheared away below the machine. It did not roll into open water. It became trapped in the worst possible place, half on failed bank, half over the cut, with the tide still turning and the material beneath it no longer behaving like compacted earth at all. That was the moment the operation stopped being routine. Back to the machine. A Caterpillar D8 of that period had the weight and torque to push extraordinary loads on prepared ground. But recovery from a bank failure is a different problem entirely. Once a crawler settles into tidal silt and broken embankment fill, its own mass works against it. Every attempt to throttle out can spin the tracks, polish the mud, and destroy what little bearing strength remains. The tractor had enough power to climb. It did not have a surface to climb on. The obvious answer was another machine. In the field, it usually is. But on a damaged sea bank, adding another heavy crawler can turn one trapped tractor into two. The recovery plan assumed the remaining shoulder still had enough strength to support a pull. The site delivered something weaker: waterlogged clay over disturbed fill, cut by seepage, with tidal scour still attacking the toe of the breach below. One of the other D8s was brought into position on firmer ground inland of the failure. Cable was rigged. The line went tight. For a moment, the trapped machine rose slightly at the nose. Then the bank beneath the recovery tractor began to deform as well. Not a full break, but enough movement to force the operator off the pull before the second machine was dragged into the same failure zone. On paper, that should have worked. In the field, it did not. Mechanically, the problem was simple. Recovery force only matters if the anchor machine has stable purchase, and the disabled machine has something solid to climb onto. Here, neither condition was fully true. The trapped D8 was trying to come up through material that had lost shear strength under saturation. The recovery tractor was pulling from a bank already weakened by overtopping and internal washout. The cable could transmit force. The embankment could not transmit stability. So the operation changed. Instead of a direct recovery, crews began rebuilding the bank around the trapped machine. More fill, more clay, more stone where available. The idea was to create a new working surface beneath and behind the tractor, then try again on the next low water window. That bought time, but only a little. Because the tide does not pause while an engineer revises the plan. When the water returned, it attacked the unfinished repair exactly where the operation was most vulnerable, at the interface between old bank and fresh emergency fill. Some of what had been pushed in held, some did not. The current found the loose edges, stripped material from the toe, and reopened part of the slope the machines had spent hours rebuilding. By the next ebb, the trapped D8 was still there, but deeper set and harder to reach. That should have ended the recovery. It did not. The machine was not abandoned immediately because the breach itself still had to be closed. And that is what made the situation so severe. The trapped tractor had become both a casualty and an obstacle inside an unfinished flood defense operation. The remaining D8s continued pushing from safer sections, narrowing the opening by degrees, while crews worked around the immobilized machine as if it were now part of the embankment. In practical terms, that meant the operation split into two parallel jobs. First, close the breach before the next major tide sequence widened it again. Second, preserve enough access and bank integrity to recover the tractor afterward. Those goals were not perfectly compatible. The fastest way to secure the bank was to dump mass into the gap and armor the closure. The safest way to recover the machine was to maintain a controlled slope and stable approach geometry. Under pressure, flood defense wins. And that was the deeper lesson of the 1953 East Coast repair work. Once a heavy crawler gets trapped inside an active tidal breach job, the machine stops being the main priority. The sea defense becomes the priority. The equipment matters. The line of water matters more. Accounts from post-flood operations across eastern England describe emergency closures made with clay, rubble, fascines, bagged material, and whatever heavy plant could be assembled quickly enough to resist the next tide. In several districts, the work continued for days under military coordination, civil engineer supervision, and local labor operating in freezing wind across waterlogged ground. The D8s were part of that larger national emergency response. Their task was brutally direct. Push enough material, fast enough, in the right place, to stop the sea coming farther inland. Eventually, the breach was closed. Not elegantly, not in one clean, decisive push. It was closed by repetition, by weight, by timing, and by the stubborn ability of crawler tractors to keep working on ground that would have stopped wheeled machines almost immediately. The trapped D8 was later recovered once the bank had been stabilized enough to support a proper pull and excavation around the failed section. But by then, the machine had already served its unintended role in the operation. It had marked the exact point where the embankment had been weakest. What failed next was predictable. Investigators and engineers reviewing the 1953 flood damage found that many sea defenses had not simply been overtopped. They had been undermined by combinations of exceptional surge height, wave attack, poor maintenance in some districts, weak sections in older embankments, and the compounding effects of erosion once a breach opened. The flood became a national engineering warning. Seawalls and embankments that had been treated as adequate under past conditions were no longer adequate under extreme surge conditions. That matters because the consequences outlived the machines. The North Sea flood of the 31st of January to the 1st of February 1953 killed more than 300 people in England and over 1,800 in the Netherlands. It damaged or destroyed sea defenses across long sections of coast. It accelerated major reassessments of coastal engineering, warning systems, emergency planning, and tidal defense policy. In Britain, it contributed directly to stronger flood protection planning and, in the longer arc of history, to the thinking that eventually produced the Thames Barrier decades later. Back to the machines. The Caterpillar D8 did what it had been built to do: apply concentrated force at low speed in conditions that defeated lesser equipment. But the machine was built for earth-moving, not for rewriting hydraulics. Under those conditions, steel met tide, and tide kept testing every assumption beneath the tracks. The site is quiet now. Many of the repaired banks were later strengthened, raised, regraded, or rebuilt entirely. The emergency works of 1953 disappeared into the longer history of coastal defense. Most of the tractors that worked those breaches are gone, scrapped, rebuilt, or absorbed into other jobs long forgotten. But for a few days on the east coast of England, 6 Caterpillar D8s stood between broken seawalls and open country. One of them went into the bank when the bank itself ceased to exist. The machine was recovered. The lesson remained. If this kind of machine history matters to you, subscribe, and if you have worked tidal ground, embankment repair, or flood recovery, tell us which part of this operation you would have trusted least: the bank, the pole, or the tide.